All right. So last day we finished and we talked about the ionic radius or radii and the atomic radii or radius. And I'll do a little review of that in a minute, but I'd like to finish ionization energy first. And then I can kind of give you a summary of them together. Okay, so first things first. What is ionization energy? Well, this is the amount of energy required to remove an electron from an ion or atom. Now, I had a student in the other class ask, what did I mean by ground state? It just means its lowest energy state, and that's something a little advanced that we don't need to worry about. Again, it just means like take an atom or ion at its minimal energy, there's no energy put into it. How much energy would we need to put into it to take an electron away? So if you break that word down, ionization energy is the energy it takes to make an ion. And remember what ions are. Ions are atoms that have lost or gained an electron. But in this case, we're talking about removing an electron. Now, the interesting thing is some atoms might lose one electron, some atoms might lose two or three electrons. It happens. So we label every time you take a electron away, you kind of change the name. So the first electron, we would say this is the first ionization energy. The second electron, it would be the second ionization energy. And the reason we give them names is that, I'll show you this in two more slides. The energy it takes to remove an electron changes after every electron you remove. In simple words, it gets harder and harder to remove electrons after you remove one. And then, I'll have it worded better in the next two slides, but it's, removing subsequent ions takes a lot more energy. And I'll show you in the next slide. So, really, honestly, this is a little bit above first year chemistry to go too into detail here. But like all you truly need to know is the trend of ionization energy, and this will help us understand why some elements form cations and why some elements form anions. That's really all we need to know today is the trend of ionization energy. So I do have an example here that this slide you definitely don't need to worry about, but I like for studying, but I do have an example here if you're curious. The energy it would take for chlorine to lose an electron. So guys, this is like a chemical reaction. Not really, but I mean, this is how we would write a chemical reaction. We have a reactant and we have what's called the products. Again, this is not the best example for that, but what I'm trying to say is the fact that this is over here on the right means it has left this atom. It's a product, it's left, it's gone, it has been removed. And the energy it takes to do that would be 1,250 kilojoules. And then per mole, we'll get into the moles and stuff in another unit, but basically this just shows that it takes a lot of energy to remove these electrons. So you don't need to worry about this slide. Let me just check the chat here. Ooh, so Warda says, is this endothermic reaction? Yes. That's exactly right. Very good. So if any of you have heard of this term before, or even if you haven't heard of this term, I guess I should say, there's terms in chemistry and physics called endothermic and exothermic. Endo, I always think of endo like indo, like inside. Endo, or like it's pronounced endo, but endothermic means the energy must be put into the system to make the reaction happen. Exothermic, think of exo like exit, or exo typically means outside. Exothermic means it releases energy. So, for example, burning propane, or if you have a lighter, near you, you can do an exothermic reaction right now. You, the combustion of propane and butane releases energy, and that's why it gets hot. That's why, we get energy from it. But some chemical reactions require energy to happen, or I should say, absorb energy, and they are called endothermic. Yeah, it does look complicated, and the reason, honestly, that this looks complicated, and Warda has a good point. It looks complicated, but it's actually not that bad. But the reason this might look complicated is we haven't even looked at chemical reactions yet. So don't worry about this slide for right now. I mean, and this won't be on a test anyways. You don't have to worry about this for a test. But maybe at the end of the year, when you're looking over your notes, if you come back to this slide, you'll be like, oh yeah, okay, we got reactants, products, we got an energy term. I know what a mole is. I know what a kilojoule is. Like, we're going to kind of build on this as we go through the course. So let me move on here. This is another slide you don't have to memorize or worry about for a test, but it's really kind of cool to look at. So let's look at our good friend down here, chlorine. These are ionization energies, meaning this is the first electron, second electron, third, fourth, fifth, sixth, and seventh. And we're looking at removing valence electrons. So like the sodium, it's in group 1. It only has one valence electron, so we can't remove, or we're not going to remove any more. Chlorine, excuse me, guys, is in group 17. So it has 7 valence electrons, which is why you can see it has all of these ionization energies for it. But look at the number. The first electron, 1200. The second, 2200. 3800, 51, 6500, then 11,000 at the end. This slide, while you don't need to study it, it is kind of good to know that every time you remove a successive or another electron, it takes way more energy, or much more energy, way more. That's not good English, is it? It takes much more energy. So that's why atoms just don't lose, 5, 6, 7 electrons easily. It takes a lot of energy for these elements to lose an electron or remove an electron. And I mean, I could go into crazy detail here. I probably won't because of time, but you'll notice that like the metals have very low ionization energies compared to the non-metals. And that's part of the reason why metals form cations. They become positive, and the non-metals form anions. They become negative. And we'll get into that a little later. So, okay, it's 11:54, and I haven't even got to the point that I'm trying to get to. All I want you to know is the trend. And the trend is written a little confusing, but I'll show you with a picture to explain this. It's pretty easy. The only problem with the trend is that you might get it mixed up with with the atomic radius or ionic radius. So let me explain the trend, and then I'll show you both. Ionization energies generally increase as we go across the periods, so from left to right, and ionization energies decrease when you go down a group. Okay, so that's not the best way to remember this, but let me show you this on a graph. This on the bottom, you don't need to know, don't worry, but it does mention that the main group elements, S and P, they have a big range of ionization energies. The transition metals in the middle, they don't range as much. The difference between the numbers aren't as big. So I'm going to check the chat in a minute. I can see some messages there. But let me just explain to you, or put together. I always do that. I'm going to start over. I always make the P block too big. think it should look like that. Okay, so there's my very rough sketch of the periodic table. So ionization energies. I'm going to show you how, oops, oh no. Hold on, guys. Okay, good. Whew, I thought I lost my drawing. Okay. Ionization energies increase in this direction. I guess if I'm going to be proper, I'll say increasing. Now, if you can remember last class, you might notice something about this arrow. This arrow is the complete opposite of atomic radius or radii. Okay, so I'm concentrating really hard so I don't mess up my spelling. The pen. Okay, and this goes for ionic too. Okay, so do you notice this is where you could see an issue on a test? They're the opposite. So you have to make sure, well, and I can kind of show you a little trick to this in the next section when I get to electron affinity, which I'll explain what that is in a minute. But yeah, there it is. So I'm going to move on from this slide in a second. So if you like, the problem is this won't be, this is not in your PowerPoint, but it will be in the video. So if you miss this, I'll have your videos uploaded today. And yeah, there it is. This is what you need to know. Okay, so I'd love to get to electron affinity, and then I'll show you this summary, and I might just get through maybe a couple of these groups really quick, but we won't finish today. That's all right. Okay, and here's a picture of the ionization energies. Again, it increases as we go up and right. All right, let me check the chat. Some funny stuff in the chat there. And Iman asking about the hydrogen bomb, nuclear bombs. I don't actually know much about that, to be honest, but it's definitely involved with manipulating atoms and not electrons. So, I mean, that's an interesting topic or question. It's definitely more physics than chemistry. Like, you know, in chemistry, we like in 2 seconds we can take chemicals and manipulate their electrons. We do it all the time, and you guys did it in the lab last week. You were moving electrons, forming new bonds. Like when you were doing the spot plate lab and you were seeing color changes and bubbles forming, we were manipulating electrons through atoms in our chemicals. So, or I guess I should say ions in our chemicals. So in chemistry, very easily, I mean, you do it in your kitchen all the time, we can manipulate electrons. But moving protons, that's definitely the physics world and not something I've ever done. But yeah, very interesting topic there. All right, I think like when you look at moving protons, you get into like fusion and fission and all this stuff. My brother, actually, he used to work here at the college. He's a physics major, I think he has his master's in physics. And he worked at a nuclear power plant in Canada for a while. So he probably knows a lot more about that than me. Anyways, okay, so I really need to get through electron affinity, because this is our last trend. And then I have a little present, because I have a summary of all the trends, which is basically all you need to know. And then just because we're a little tiny bit behind, I might do a couple of groups, and then that's it. Okay, so let me get through my last trend. So remember your trends, guys. There's density, atomic radius, ionization energy, and electron affinity. And most of them are on this slide, except density. All right, so last trend. What is electron affinity? Well, okay, the fancy definition is, I'll read it, but I'll give you a better and easier one. Electron affinity is the energy change accompanying the addition of an electron to an atom, or a gaseous atom, but just say to an atom. So let's think about this more simple. The word affinity in English is like how much you are attracted to something. Like if I have an affinity for cats, that means you like cats better than dogs. If I have an affinity for dogs, I like dogs better than cats, right? If you have an affinity, it's like an attraction, or you like it, or well, I guess an attraction is probably a better word to say. So electron affinity is kind of a number. It's the energy related in how much this atom is attracted to electrons. And you'll notice, I think it was Yusra or Warda in the chat. This would be exothermic, but again, don't worry. This is a lot of information that you guys don't need to know for the test. You just need to know the trends. Yeah, so there you go. And the negative energy term shows that energy is released. That's where the whole exo business comes in. But again, don't worry about this. Basically, electron affinity it's the energy change accompanying, or the energy change when an electron is added to an atom. So it's like.
Could you write this yourself, this definition?
Sorry?
Could you write this definition? The electron affinity?
Yeah, well, the definition is this: the electron affinity is the energy change, when an electron is added to an atom. That's the easy one. Sorry, that word is added. Okay, so electron affinity is the energy change when an electron is added to an atom. But what I really want you to think about is when you look at these energy changes and when you look at the numbers are representing the attraction, or how easy it is, I should say, to add an electron to the atom. The easier it is to add an electron, it's a bigger chance that this thing would form an anion. Okay, and again, the whole point of this, I know this kind of looks complicated, but the whole point of this is eventually we want to wrap our heads around, why do metals form cations and why do nonmetals form anions? And it's all about this. It's all about electron affinity and ionization energy. It's a lot easier to add an electron to a nonmetal, and it's a lot easier to remove an electron from a metal. And all that together is what gives us ions. And ions are what makes us have so many different chemical bonding. And Abdul Halim says it's about becoming more stable, and you're so correct there. It's easy for chlorine to gain one electron because it wants that electron. It wants to become more stable. And anybody listening who is like, what are you talking about? We're going to get into this in the next unit. We're going to talk about what makes an atom stable. And it's all about the electrons. This course is all about building and building and building. And I think by chapter 3, this should all kind of come together. Okay, so in general, electron affinity increases as you go from left to right across a row. And it also increases typically as we go up as well, which isn't written down there. Okay, so this is it, guys. I've spent probably 30, 40 minutes talking from today and yesterday, and this is really all you need to know. Now, you'll notice there's one thing missing on this slide, and there's one thing extra on this slide. The thing that's missing on the slide is I don't mention density. So I'll just make a little note here. Density.
Mr. We don't have this this slide.
No, this is a picture I added, so it'll show up on the YouTube, but if it's not in the notes that you printed, you can take a screenshot or maybe write it down. This is a new picture that I found the other day, and I figured I could add it in for you instead of drawing it myself. So if you have your notes printed, this isn't there. So you might want to write it, take a picture. It will be on the YouTube, so you can always look at this on YouTube as well. Again, if you don't have if you want this, you could write it down right now. It's pretty easy. Just kind of make like a little fake periodic table, right? And then you can put in the arrows and the words. You can write that on your notes if you have it printed. I'll leave this slide up for a few minutes. So this slide is missing the density. Density increases as atomic number increases. And you see a word here maybe on the slide called electronegativity. We are going to talk about that later. Okay. I mean, this is obviously not my image. I took it from Google. So I didn't want to edit it because honestly, this concept of electronegativity is definitely important, and we'll talk about that later. So I'll leave that up for a minute if you guys want to copy it down or take a picture or let it kind of absorb into your brains. Warda had a good question, and okay, that's it. She said, what is the magnitude of electron affinity? We did this back in chapter 1. Magnitude is the size of the number. So when I say, the magnitude of electron affinity, I just mean the size of the number. So the amount, Abdul imperfect, the amount, how big is the number? Some of these definitions are pretty wordy. I do apologize for that. All right, cool. So it's 12:07. Oh man, I got the coldest glass of water here. It's so good. Okay, it's 12:07. I want to finish in a couple minutes, but we are a tiny bit behind because of all the questions. And again, that's a great thing. I will always take being behind versus a class that has no questions. So I do appreciate all the questions. I just want to maybe introduce the finale of chapter 2, the last kind of section, and then on Monday we'll finish this. Okay, so guys, this picture, this is a good study guide. You make sure you look at this. It'll be on the YouTube video. Again, you can take a picture of it now if you want, but this is, or screenshot, this is huge. Huge. For the people who have their notes printed, I hope you had a chance maybe to write it down. And if you didn't have a chance to write it down, but you want to, you can check my YouTube video later this weekend and maybe pause it here and write it down. All right. So Warda has written the table down. So if anybody wants that sent to them, you can ask. Put it in the, yeah, there you go. Okay, cool. You guys are a good group. All right. So guys, let me get this finished because I got another class and I think my dog has to go out for a minute. Let me just do alkali metals. Yeah, okay, let me do alkali metals and then that'll be it. Basically, the last part of chapter 2, I'm going to look at a couple of groups. Group 1, group 2, I think I'm going to look at group 6, 7, and 8, and we're just going to learn some fun facts about each of these groups. And these are just some things you might need to know for like multiple choice type questions. Okay, so group 1A, these are alkali metals. They're soft metallic solids. And you saw one of these in lab 2 where I took sodium, which I cut with a knife. This, by the way, is a very nice brand of knife. I like to cook and I like kitchen things. And this is like my dream. One of the nicest types of knives that I've ever used, but I don't own one. Anyways, um, sorry, but you can cut these metals with a knife, so it's not like iron or copper. You need something a little sharper or a lot of heat. These are soft metals. The name, and I can't verify this, and I'm not saying that alkali is a word in Arabic today. I just mean 1,000 years ago, or 1,500 years ago. I don't know the timeline or anything, but a long, long, long time ago, the word it stems from the Arabic word for ashes. And again, I cannot verify that, but that's what most of the research I've done has said. They are found only in compounds in nature, never in their elemental forms. So, not unlike oxygen or nitrogen or even carbon, where you find them in pure elemental forms, they are often found only in compounds. So we have to kind of extract them, refine them to get the pure chemical. You don't need to know this. Get rid of him. They have low densities and melting points, and they have very low ionization energies. Now, think about that. They have low, the energy it takes to turn them into an ion is low. Or sorry, I said that wrong. The energy it takes to lose an electron is low. Easy to lose electrons, and that's why they are cations. Oh man, that looks like cations, doesn't it? All right, it's easy for these guys to lose electrons, so they form cations typically. This table just shows some properties. You guys don't need to memorize any numbers or anything like that, but you should know that they do have low ionization energies because they are on the left of the table. These reactions are famously exothermic, meaning they famously react with water. Hamza, if you have to leave early, that's no problem, sorry. I'm almost done now anyways. So we did this one in the lab. It looks a little nicer here. Oops. It looks a little nicer there. I think they're using a lot more than I did. But look at the colors, guys. We have like white, we have orange, we have purple. These elements give off different colors when they react too. It's pretty cool. They also produce bright colors when placed in flame, and you can actually use something called a flame test to see what type of metal you're dealing with. You can burn each of these samples, and the color of their flames will tell you what chemical it is. Isn't that cool? Like, look how pretty. If we had potassium, we unfortunately don't have any pure potassium in the lab, so I can't do this for you. But if you burn these things, they're all different. Like, look how pretty. Actually, lithium is amazing. Look at that. So pretty. Bright, bright red. So there's something called a flame test where you can burn these ones. And Kevin, that's funny. Colors. I like colors are kind of my weakness too. I dabbled in. I like to like research a lot of things like graphic design and stuff to look at like colors and how colors match for documents. And I'm a big fan of colors, I gotta say. I always have been, even when I was a little kid. I love colors. Not a good colorer. I could never stay inside the lines, so that's why I'm not a graphic designer, but I like the idea of colors. Okay, guys, it's 12:14. I want to finish here. I kind of wish we could have got a little further, but oh well, that's okay. It doesn't matter. We're still doing okay for time. So I'm going to stop my recording. This will be up on YouTube today, inshallah. And I will answer any questions you have in the chat. So if you want to go, have a great day.
Sir?
If you have questions, let me know.